Hello, class. Now we're going to talk a little bit about confidence intervals. So clearly, null hypothesis significance testing has some problems. Clearly, it's not perfect. So how might we either fix null hypothesis significance testing or supplement it by including something that gives us some more information that leads us not to this dichotomous thinking of there is an effect or there's not an effect. So one example of something that we might do would be to conduct confidence intervals. Now, as I mentioned before in Jeff Cummings' book, The Understanding the New Statistics, you can't really read that backwards, but one of the things that he suggests is confidence intervals. There's nothing new about a confidence interval. In fact, Jerzy Neyman from Neyman-Pearson null hypothesis significance testing was one of the first people to suggest the use of confidence intervals. So what is a confidence interval? Well, when we are estimating using a sample to infer what happens in the population, we can try to infer what's the actual population mean. And there's a couple ways that we could do this. One is with a point estimate. A point estimate is a single value that we think is the best guess that we have of what the true population parameter for the mean is. All right. So, for instance, if we want to find the true population mean of, I don't know, psychology test scores, I might randomly sample 20 people, give them the test, and then that sample mean I'm going to use as my point estimate for what I think the true population mean of psychology test scores are for whatever the population is, right? Obviously, the sample mean is the best thing that we have to infer what happens in the population. So point estimates are good. If we have to pick one value, the sample mean is probably the best predictor of what the true population mean is. But it doesn't give us a degree of uncertainty. Okay, we don't know how uncertain our estimate is. It could be the case that we sampled thousands of people and our uncertainty is very low. We think that our sample mean is a very good measure of what the true population mean is. It could be that we just ask 2 people to do the test, and so our uncertainty is very great, and we don't know if this single estimate, this point estimate, does a good job of capturing what the true population mean is. So instead of using a point estimate, we might supply an interval estimate. So we give a range of possible values. So, well, we think that the true population mean is from here to here. Okay. So for instance, if you look at political polls, which you're probably inundated with given the election coming up in a month or so, a lot of times those have a margin of error of 3%. Okay, so the true favorability of this presidential candidate is somewhere either plus 3 percentage points or minus 3 percentage points. So they give you an interval where the true population mean might fall. Okay, there's a few different ways to calculate interval estimates, but the really only way that we're going to talk about, and by far the most popular way of developing an interval estimate, is confidence intervals, or R confidence intervals. Okay, confidence intervals are based around a sample statistic, particularly a mean. So we're going to build our confidence intervals around our sample means. Okay, so and the way that we interpret confidence intervals is tricky, and many people get the interpretation of them wrong. So here's the correct interpretation of what a confidence interval is. If we were to repeat this experiment, repeat this study, repeat this sampling practice again and again and again an infinite amount of times, the confidence interval that we create, okay, each single time around the sample mean, 95% of those confidence intervals will include the true population mean. Okay, 95% of the times, the confidence intervals that we create will include the true population mean. That's how we interpret a confidence interval. You will see sometimes in reputable statistics books, sometimes in other stats classes, incorrect interpretations of what a confidence interval is all about. but that is the correct interpretation, and please do not forget that. There are many ideas very similar to confidence intervals, and you'll see these all over the place. So sometimes you'll see them called confidence intervals, sometimes you'll see them called interval estimates. A lot of times for political pollings in particular, you'll see them called margin of error. Many of these are based off of the same idea. There are many different confidence intervals that you see, but two of the most common are 95% confidence interval. This is the one that is most common. Okay, why is it most common? Because there's a 5% situation in which we do not include the true population mean. And so that is very similar to our type 1 error rate. So that's why people enjoy this confidence interval. And we have our 90% confidence interval. All right, we see those frequently. Okay, so how are we going to calculate a confidence interval for when we have the true population mean and the true population variance? So a situation very akin to a one sample z-test. All right, and how we calculate confidence intervals will change depending on which information we have. So we're going to look at confidence intervals right now just for when we have a one sample z-test, a situation where we have one sample, a population mean, and we have what the true population variance is. All right, so here's what we do. Now, we need to find two scores. Okay, we need the upper bound and the lower bound of that interval. The lower bound, we're going to first get our sample mean, and we're going to subtract from that sample mean. So the lower bound is obviously going to be less than the sample mean. Okay, we're going to subtract it by a particular z-score. And this z-score is going to be selected based off of how confident we want to be. Is it a 95% confidence interval? Is it a 90% confidence interval? What is the level of confidence for this interval? That z is going to determine that. And here we have, well, let me ask you guys, what is this? We have the population parameter for standard deviation, but it's not any old population parameter for standard deviation. Okay, it is the population parameter for standard deviation of a set of means. This has a special name. It is the standard error of the mean, and hopefully you were thinking about that. That's what this thing is. So we take the mean, we subtract it from a particular z value, depending on how the confidence level, multiplied by the standard error of the mean. The upper bound is exactly the same thing, but instead of subtracting the z-score multiplied by the standard error of the mean, you add it. Okay. Why do we need two calculations? Well, we need the lower bound and the upper bound of this confidence interval. We need a value that's lower than the sample mean and a value that's higher than the sample mean. So let's do an example here, and let's go back to our Starbucks example from the previous module. All right, you might recall that these researchers were interested in, after we require people to, or Starbucks, to post the calories of all their drinks, does this change how many calories are consumed by the average person? So we've got our true population mean right here from before the law was enacted. We've got the true population standard deviation. The number of subjects that we sampled is 1,000, and the sample mean for after we enact the law is 232 calories. Okay, so what we're trying to do for a 95% confidence interval, we're trying to find an interval for the sampling distribution, okay, that 95% of the means, okay, would fall in this range, okay. 95% of the time, the means would fall in this range. Okay, well, to set this up, since we have, we might make an error below and we might make an error above, we're going to set the percentage of time that just due to chance we'd get something that's less than that to be 2.5%. And same thing with above our interval estimate. All right. So we need to find the z-scores, the z-values in which 2.5% of people score above it and 2.5% of people score less than that. All right. This is a z-value that we've already looked at. Okay. In fact, the z-value is 1.96. Okay. But that's for the standard normal distribution. All right. Standard normal distribution where we have a mean of 0 and a standard deviation of 1. So what we need to do is we need to take these z-scores, okay, these z-values, and convert them back to the actual distribution. Okay, not the standard normal distribution, the particular distribution that we're interested in. Okay, so to do this conversion, we're going to calculate the confidence interval with using the formula that I showed you earlier. Okay, so the first thing that we need to do is to find the standard error of the mean. We have the true population standard deviation is 201. We divide that by the square root of n, which is 1,000. This gives us a standard error of 6.356. All right, for our lower bound, we're going to take the mean. The sample mean is 232 minus 1.96 multiplied by the standard error, and that's going to give us a value of 219.54. We're going to do the same thing, but this time we're going to add that value. So we're going to get an interval, a confidence interval in particular, of 219.54 and 244.46. So that's our confidence interval. Now, this gives us a whole lot more data than just the single point. All right, it gives us a range of values in which we think that the population mean might be within this range of values. Okay, again, if we were to conduct these confidence intervals millions of times, 95% of the time, the confidence intervals that we calculate will include the true population mean. All right, that's the correct interpretation. But the interval estimates give us a whole lot more data than just the point estimates. We get the degree of uncertainty here. And that's very helpful when we try to make decisions or try to see if there is truly a difference between two sample means. When we try to see if there's truly a difference between this condition and that condition. If we get the confidence intervals, we can see, do those confidence intervals overlap with one another? In actuality, there probably is not too much of a difference between them. Or if those confidence intervals are really wide apart from one another, and we can make a judgment call about maybe it's the case that those are truly different at the level of the population. All right, so here's what's going on when we create our 95% confidence interval. The 1.96 is chosen directly for a 95% confidence interval. Guess what we choose if we're doing a 90% confidence interval? The value is 1.645. Again, the other value that I've asked you guys to memorize, particularly when we're doing a one-tailed one-sample z-test. All right, so for a 90% confidence interval, it's 1.645. For a 95% confidence interval, it is 1.96, just the way that the standard normal distribution ends up working out. There are many incorrect interpretations of the confidence interval that I want you to look out for. Okay, this first one is the most subtle. Many people incorrectly assume that a 95% confidence interval means that there is a 95% chance that the true population mean is in the interval. And this is close to correct, but isn't actually correct. All right. Strictly speaking, the true population mean is either in it or it's not in it. Okay. So you can't say, well, there's a 95% chance. No. It's either 100%, because yes, the true population mean is within the interval, or it's 0, and that we didn't capture it. So this is close to accurate, but not an accurate interpretation. Here's some other really bad interpretations of confidence intervals that you'll see made frequently. So sometimes people say that they're 95% confident that the population mean is in the interval. And this doesn't make any dang sense. I was about to use a bad word, but I censored myself for you guys. No, that's 95% confident. I don't even know what that means. Okay, and I have seen some statistics classes that teach you this interpretation. So it's bad. What does it mean if you're 95% confident? I don't know. You can be 100% confident and be wrong all the time. Okay, you can be 15% confident you've got the correct answer, and you could have the correct answer much more than that. So I don't know what this is actually getting at. This is the incorrect interpretation. Sometimes people say that a 95% confidence interval means that 95% of the data, 95% of the scores fall within the interval. This is not a correct interpretation as well. Okay, and some people say that if we were to calculate if we were to do the experiment again, that the new sample mean that we calculate, that we find, would fall within the confidence interval 95% of the time. That's not correct either. Okay, so be mindful of these incorrect interpretations of confidence intervals. So again, what is the correct interpretation of a confidence interval? If we were to do this study again and again and again and again, and calculate a confidence interval each single time, calculate confidence interval with this sample, with this sample, with this sample, we would find that the true population mean would be in 95% of those confidence intervals. So for instance, here we are looking at creating confidence intervals in a particular study. In this situation, we know what the true population mean is, and we see that the confidence intervals, the majority of them, in 19 instances, they cover the true population mean. But there's this one rogue thing right here. There's this one rogue study that does not include the true population mean. So 95% of these confidence intervals include the true population mean. In the long run, if we were to do this infinite amounts of times, 95% of the time, the confidence intervals would encapsulate the true population mean. Okay, get that interpretation in your head. So what are things that vary here? Well, let me repeat that. That was not a good introduction here. What are things that change the confidence interval? So the easiest thing that changes the confidence interval is the number of subjects that we have. Okay, the more subjects that we have, the more confident we are as to where the true population mean is. No duh, the more you sample, the less sampling error is going to matter. Okay, the more you are likely to get at what the true population mean is. So we can see here that as the number of subjects increases, the confidence interval gets smaller and smaller and smaller. Let me return to our calculations. Okay, the standard error matters. Okay, and remember, in the denominator of the standard error is n, the number of subjects that we have. The larger this number is, the larger n is, the smaller our standard error is going to be. The smaller our standard error is going to be, the smaller this expression z times the standard error is going to be. Okay, and the smaller these two values are, the tighter this confidence interval is going to be. The smaller it is, the more confident we're going to be. Okay. The other thing is that the percentage confidence. Okay, so the higher the confidence interval, the wider the interval is going to be. Okay, because the more certain we are that 99% of all the confidence intervals that we could create would include the true population mean, it's going to be a very wide interval. Okay, the less confidence, the shorter that interval is going to be. Some people do null hypothesis significance testing with confidence intervals. So what you could do is calculate a 95% confidence interval. And if the true population mean, if the population mean that we're comparing things to is outside of that interval, we reject the null hypothesis. If it's within that interval, we retain the null hypothesis. And that way of doing the statistics is exactly the same as the one sample z-test that I've shown you guys before. But if you're trying to come up with a dichotomous decision, you either reject or retain the null hypothesis, you're getting rid of all the useful data that is within a confidence interval. So yeah, you can do that. And in fact, when I was taught confidence intervals, that's how it was explained to me. Well, you can do it the one sample z-test way, or you can do a confidence interval and see if the population mean falls outside of that confidence interval. That'll get you the same thing. But the confidence interval has a richer amount of data to it, has a richer amount of information to the confidence interval. That's what I'm going for. Okay. Confidence intervals you're going to see very frequently in graphs, in bar charts, in line graphs, and they're a good way of showing to the reader or the degree of uncertainty that you have, okay? Because we could show you a difference, okay? And you don't know if it's a small difference or a huge difference, right? Remember, some people might lie to you by changing the scale of a particular graph, okay? And that happens very frequently, as we've seen. To give the reader some indication about the uncertainty, we might take a bar graph or take a line graph and construct a confidence interval around the particular points so that the reader has an idea of the uncertainty. But be mindful, sometimes these bars, which are called error bars, sometimes they are confidence intervals. Sometimes they are standard errors. So here, for this graph that I found on the internet, the error bars here represent a standard error of the mean. So one standard error above the mean, one standard error below the mean, okay? The confidence interval, if we were doing a 95% confidence interval, would be pretty much twice this length, okay? So be mindful about the interpretation. This is actually from one of my papers, and I've cut off the description, but it says that these are 95% confidence intervals. So make sure that you understand what the error bars are representing when you're looking at papers, when you're looking at articles, okay? Sometimes, sometimes the error bars will be based on standard errors. Sometimes they'll be based on confidence intervals. Sometimes people like to look and see whether or not the confidence intervals or error bars overlap. So if there is overlap, they say that there is not a statistical difference. When there is overlap, there's not a significant difference. When there is no overlap between the error bars, they say that there is a statistical difference. And here's the fun fact. In certain cases, that is a correct conclusion, okay? In certain experiments, if you see the error bars overlap, you retain the null hypothesis. If the error bars do not overlap, you reject the null hypothesis and say there's a difference. But that's only in certain cases, all right? So don't rely on error bars telling you if there is a significant difference. They do tell you a good degree about the uncertainty of the experiment and the amount of variability in the experiment. So in this way, confidence intervals provide a richer amount of data than traditional null hypothesis significance testing. So yay, that's better. That doesn't completely fix null hypothesis significance testing, but it does give us some more information, and that's good, okay? So let us stop there, and in our next video, we'll talk about effect size and power. Thank you guys, and have a good day.